Welcome to our practical session on the variation in acceleration with changing force. In our recent lessons, we've delved into Newton's second law of motion, which elegantly states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. You've gained a clear understanding of how different forces affect the motion of objects and how acceleration is calculated when force and mass are known. Today, we take this understanding a step further by engaging in a hands-on investigation to observe how acceleration varies when we change the force applied to an object or the mass of the object. We're almost ready to dive into the practical. Before we do, let's quickly flesh out its core importance. First, this experiment directly taps into the principles that engineers and designers use when creating a vast array of technologies, from automobiles to spacecraft. Engineers must precisely calculate acceleration profiles for safe and efficient vehicle design, ensuring that structures can withstand various forces. On a more immediate level, recognizing the principles of forces and acceleration can demystify everyday phenomena, such as why cars accelerate differently based on engine power and load, or how athletes might use these principles to optimize their training and performance. With this in mind, let's move on to the practical. As we mentioned in the introduction, we'll be investigating how both force and mass affect acceleration. Accordingly, we need two different experimental setups. We'll start with experiment 1, which requires a setup to investigate the effect of force on acceleration, whilst keeping the mass constant. Sam, what do we need?
For this, we will need a toy car, a track with set distances measured at regular intervals for which we require tape, a string, a set of weights, a pulley and a video recorder. A phone will work.
Okay, now for the setup. We first set the pulley at the end of the track and thread the string through it. We then set the toy car at the beginning of the track and attach it to the string. Finally, we will attach a 100-gram mass to the other end of the string. Ensure that someone is ready to hold the toy car down so that it doesn't move. We only want it to move when we are recording. The role of the mass on the end of the hanger is to provide the force which will be acting on the toy car. But how do we get from a mass on the end of a hanger to force? Well, we know that weight equals mass times gravitational acceleration. Since the gravitational acceleration on Earth is 9.8 meters per second squared, and the mass on the hanger is 100 grams, which is 0.1 kilograms, then we can calculate the weight by doing 0.1 kilograms multiplied by 9.8 to find that a 100-gram mass will have a weight of 0.98 newtons. We can do a similar calculation to find that an 80-gram weight will have a force of 0.78 newtons on Earth, and so on. Therefore, when we are filling in our table, we can use the following conversions between mass and force. Just to make this easier for us to plot on our graph, let's round each of the forces to one decimal place like this. Okay, back to the practical. We have our toy car at the start of the table, with a 100-gram mass on the hanger, which is providing a force of 1 newton. Once we're ready and the string is taut, we press record on our phone and release the toy car. Because there is a resultant force acting on the string, the car will accelerate towards the end of the table. We need to record the time that it takes for the car to pass each distance marker we have marked on the table. So to find this, re-watch the footage and record the time at which the car crosses each interval. Write these times in a table. Once you have done this, we should rerun the experiment 2 more times to increase the reliability of our results. When we have done 3 trials for this force, we can calculate the average time it took to reach each distance by finding the average time across the 3 trials. Once we've recorded this data in our table, we turn to the next stage of our experiment. Now remember, we want to change the force applied to the toy car whilst keeping the mass constant. Since the toy car is connected to the hanger by the string, we need to keep the mass of this entire system constant. This means that when we add or remove mass from the hanger, we need to add or remove mass from the toy car too, to ensure that the mass is constant throughout. In this case, let's remove 20 grams of the mass from the hanger to reduce the force that is acting on the toy car. Remember, we now need to add that 20-gram mass to the top of the toy car to keep the mass of the whole system constant. This allows us to isolate force as an independent variable. Now we repeat the process again, but with a force of 0.8 newtons, recording the time it takes the car to pass each distance marker. Remember, for each force, record 3 trials and calculate the average times for each distance trialed. Once we have calculated the average time it takes to travel each distance interval for each respective force, we can record the information in a table like this. The table shows the simplified data for how long it takes to travel the final interval on the table, which is 20 centimeters. Once we find the average time taken for this interval, we can find the velocity for this interval using displacement divided by time. For example, when the force is 1 newton, the car travels the final 20 centimeter interval in an average of 0.18 seconds. Using the equation, this means that the car had a velocity of 0.2 meters divided by 0.18 seconds, which equals 1.11 meters per second. Using this method, we can calculate the velocity of the car at all the different levels of force. Now we can analyze this data. Remember that Newton's second law tells us the relationship between force, mass, and acceleration. We know the mass because this is the mass of the whole system, which we kept constant throughout. We also know the force applied for each of our experiments, which was 1 newton for the first experiment. And then we progressively reduce this to 0.8 newtons, 0.6 newtons, and so on. So, to confirm the relationship we see in Newton's second law, we now need to calculate the acceleration of the car. To do this, we can use the equation. Acceleration equals change in velocity divided by time. Recall that we just calculated the velocity of the car in the final 20 centimeter interval. This can represent the final velocity. Next, we know that the car was stationary before we released it, so the initial velocity is 0 meters per second. Finally, we recorded the total time taken. We can therefore create a table with all this information and calculate the acceleration using it. For example, when we have 1 newton of force, the change in velocity is 1.11 minus 0, which equals 1.11. When divided by the time taken, which was 0.55 seconds, we calculate an acceleration of 2.01 meters per second squared. Now we can graph this data to better understand the relationship. In this case, we want force on the y-axis and acceleration on the x-axis. Now this seems to be counterintuitive because we usually put the independent variable, which is the variable we have changed, on the x-axis, and in this experiment, the independent variable is force. However, in this case, swapping the variables around helps us to see an interesting result. Now that we have plotted these points, we can see that we have a linear relationship between the force and acceleration. This is exactly what Newton's law tells us, that acceleration is directly proportional to the force applied. But we can also see something else interesting. Let's find the gradient of the graph. In this case, we get 0.497 kilograms. Now remember, Newton's law states that force equals mass times acceleration. We can rearrange this to get force divided by acceleration equals mass. Well, in our case, this is exactly what the gradient is. So the gradient is showing us the mass of car and the hanger used in our experiment. If you now measure the mass of the car and the hanger, we find this comes to a total of 495 grams. So we can see that the gradient of our data, which is 497 grams, is almost exactly equal to the 495 gram mass of the car and hanger. But why is there a slight difference between the mass we have calculated from our data, 497 grams versus 495 grams? Well, that's because Newton's law assumes that there are no external forces acting, and in this case, that means no friction or air resistance. In our experiment, there is some friction between the car and the table, and there is also air resistance. And it is these external forces that explain this slight discrepancy between the theory and our experimental results. Nevertheless, the data from this experiment has verified Newton's law that F equals ma. Now let's turn to our second experiment. The setup here is almost identical to our first experiment. But for this experiment, to save us some time doing calculations, we will use light gates and a computer program which automatically calculates the acceleration of the car for us. It doesn't matter which approach you take here, as long as you have some data on the acceleration of the car by the end of the experiment. So, just like last time, we set the pulley at the end of the track and thread the string through it. Again, we place the toy car at the beginning of the track and attach it to the string. Finally, we will attach our 100-gram mass to the other end of the string. As with the last experiment, we ensure that someone is ready to hold the toy car down so that it doesn't move. We only want it to move when we are recording. Again, we release the car and our light gates and attach computer output the acceleration. Record this data in your table. After we have repeated this 3 times, we can calculate the average acceleration. Since this experiment wants to find the effect of mass on acceleration, once we've completed the first trio of trials, we increase the car's load by adding another 20-gram mass, thereby observing how this change affects acceleration. We repeat this process until the toy car has an additional 100 grams of mass applied to it. Remember, this time we keep the weight on the other end of the string constant. This is because we want the force to be the same in each test. Once we have completed 3 trials with each mass on the car, we record our data in a table like this. Newton's second law of motion tells us that acceleration is inversely proportional to mass. To see if our experimental data fits this, we should add a column to our table which finds 1 over mass. Once we have filled in this data, then we can plot 1 over mass against acceleration on a graph to check if the relationship between mass and acceleration is inversely proportional. So let's use this data to plot a graph. On the x-axis we have 1 over mass. On the y-axis we have acceleration. Now let's plot our points. We can see that we have a perfectly proportional relationship between 1 over mass and acceleration. This supports Newton's second law of motion, which states that mass is inversely proportional to acceleration. Again, if you have any slight differences in your results, so the relationship isn't quite perfect, this is likely due to air resistance and friction in our experiment, and in some cases, human error in measurement. Nevertheless, as before, this experimental data shows F equals ma in action. Great work, that's the end of our practical. Today we saw Newton's second law of motion in action. In our first experiment, we showed that with constant mass, an increasing force leads to an increase in acceleration. In our second experiment, we showed that an increase in mass with a constant force leads to a decrease in acceleration. Through both of these, we verified Newton's law that force equals mass times acceleration. We also learned that small differences between experimental results and the theory can be attributed to external forces such as air resistance and friction, as well as measurement error.